Hello and welcome to our first lesson on reversible reactions and dynamic equilibrium. This is for foundation and higher tier. In previous lessons, you have learned that a chemical reaction is defined by making something new and is difficult to reverse, and that is almost always the case for most chemical reactions. However, there are some chemical reactions that are reversible, and we showed this using the split arrow. If you look to the top middle of your screen, you can see an arrow where half of the arrow is going in one direction. We call this the forward reaction, and the other half is going back towards the reactant side, which is the reverse reaction or the backward reaction. So what we have here is a situation where reactants react together to make something new, the product, and then that product decays or reverses the chemical reaction to become the reactants again. We've seen this in class using the blue bottle experiment. You can see the GIF there. When the person shakes up the bottle, it becomes blue. That's because it's reacting with the oxygen in the bottle. It becomes blue, and then slowly the oxygen gas escapes again back to the top of the bottle and it reverts to its transparent colour. Reversible reactions. So here is another example that you may have seen in class. We have hydrated copper sulfate, that lovely blue colour that we're very familiar with. The hydrated means that it has water with it. But if we heat it up, the copper sulfate loses the water, so the water evaporates and is chemically reduced to become this white powder, anhydrous without water, copper sulfate, and the water is separate. Now, the next thing you need to know about reversible reactions is if the forward reaction, for example, is endothermic, so it's getting colder, you would expect that the reversible reaction, the reverse, is exothermic, so it's getting hotter. Likewise, you would expect if this is the natural higher pressure going in the forward reaction, you would expect the reverse reaction to be lower pressure. You don't need to know any more than that at this point. You just need to recognise that they are opposites, and you would expect if the forward reaction was one way, the reverse reaction would be the opposite way. That can change, so it might be that the forward reaction is exothermic and therefore the reverse reaction is endothermic. So just be careful that you don't assume that the forward reaction is always endothermic. It could be either or, and it could be higher pressure or lower pressure. With the anhydrous copper sulfate here, then it is a reversible reaction because if we add water back into the chemical, you get the blue copper sulfate back again, the hydrated copper sulfate. And again, I could take that, I could heat it up and it would go white again, and then I add water and it goes blue again. Let's move on to dynamic equilibrium. So the word dynamic means that something is constantly changing. Your most dynamic teacher will be the teacher that climbs on desks and is always moving around and throwing their arms around and demonstrating very enthusiastically. And you would say that they are dynamic. Equilibrium, however, means that something is balanced. So it's even, it's equal. So you have a situation here, dynamic equilibrium, where you are describing a chemical reaction as both constantly changing and balanced. How is that possible? Well, let's look at this chemical reaction here. I can tell it's a chemical reaction because I've made something new on the product side, and I can tell it's reversible because I have the split arrow in the middle there. So how is this reaction dynamic? Well, reactants are making products, and at the same time, products are making reactants. It's constantly changing, and so it's dynamic. But how is it balanced? How is it at equilibrium? Well, the thing to note is that the forward reaction is happening at the same rate as the backwards reaction. So just as reactants are making products, the products are also making reactants at exactly the same rate. And so overall, we have a balance. Now, this only works within a closed system. So as soon as I start to lose gases that have been made or add atoms in, it's going to start messing around with the results. We're not going to be able to get dynamic equilibrium. So it has to be within a closed system. If you need any more support on explaining dynamic equilibrium, there's a couple of really good videos here showing the practical that we do in class sometimes. You'll notice though these beakers do not have the same amount of liquid. So if that left hand side is reactants and right hand side is the products, it stays like that. So you could have an uneven amount, but that amount would stay the same. And if I've confused you, have a look at the video and it will make a lot more sense. Okay, so let's check our knowledge. If you'd like to pause the video, you could just write the missing words just to check your knowledge, have a think about it, and then unpause the video and we'll go through the answers. Okay, so dynamic equilibrium is reached when the forward and the backward reactions occur at exactly the same rate. Be careful with that. Speed, time, they're not acceptable. Rate is how much per second. It's a very specific answer. Rate of reaction. This must happen in a closed system where the chemicals cannot escape. At equilibrium, the rate of the forward reaction equals the rate of the backward reaction. They are equal. The concentration of reactants and products are constant, but not necessarily equal. And this was the idea I was showing on the last slide about those beakers having different amounts in. If they started off with one having more than the other, it will remain that that same one has more than the other. So it's a constant amount, but it doesn't necessarily mean they have the same amount. Okay, again, pause the video, have a go at these questions and then unpause it and we'll have a look. Okay, so the first question, apply. So we're applying our knowledge. Explain, so keyword, your command word, you are going to give a reason. So give a reason why dynamic equilibrium can only occur in a closed system. So what have you said? Something like this, hopefully. If reactants or products can escape the system, they cannot be constant. Make sense? Our connect then is linking ideas. Explain, so give a reason, what is meant by the concentration of reactants and products are constant, but not necessarily equal. What does it mean? It means the amount of reactants will stay the same, the amount of products will stay the same, but they may not be the same as each other. Okay, so pause the video and let's have a look at this exam question. So hopefully you've read it and had a look, and you'll notice that actually a lot of the information is not particularly relevant to the question. Don't ever be put off by all the information. Read the question, you might be able to answer it. The question is, what is meant by dynamic equilibrium? Two things, 2 marks available. So here is the answer. You got 1 mark for mentioning that it's a closed system, and you get a 2nd mark for saying that the rate of the forward reaction is equal to the rate of the backward reaction, or words to that effect. Again, have a go at this multiple choice question on dynamic equilibrium. Okay, so reversible reactions in a closed system reach a dynamic equilibrium. At equilibrium, which statement is correct? Well, it's going to be this one here. Rate of the forward reaction is equal to the rate of the reverse reaction. Okay, have a go and then unpause the video. So this is one that we were looking at earlier on in the video. A student heated some blue copper sulfate crystals. The crystals turned into white copper sulfate. The blue copper sulfate had to be heated to change it into white copper sulfate. State whether the reaction was exothermic or endothermic. So it's endothermic because you're having to add heat. Oh, it says explain your answer, so give a reason. It takes in the heat energy, so it's taking in that heat energy that you're adding and needing it to cause that chemical reaction. Okay, so this is the second half of the question on copper sulfate. Pause the video and have a go. So the word equation of this reaction is shown below. What does the symbol mean? Well, you wouldn't even know about that chemical reaction. Always have a go, guys. You know that symbol means reversible. How could the student turn the white powder back to blue? Well, if I look at the equation, the white powder, it says plus water. The water's been taken out. Or if I add the water back in again, I'm going to get blue copper sulfate. Okay, that is the end of the foundation lesson. If you're higher, you do need to find the lesson on Le Chatelier's principle. I hope it's been helpful. have a go, and always, as always, guys, always have a go at the questions. You might get it right.